Okay, I wanted to make a video working another system of linear equations problem without using many matrices, and this time we're going to see what happens when we have a dependent system. It's still consistent, meaning that there is a solution, but there are infinitely many dependent solutions. So let's see how to recognize when that happens and what to do. So first step, as usual, if you're not using matrices, when you're approaching these systems, you're trying to rewrite it in what we call triangular form by eliminating one variable and then back substituting to find the other two. So you first need to pick a variable that you like to eliminate. Honestly, all of these are good options, but most students typically choose z. So just to be like most students here, I'm going to choose to eliminate the z variable. In order to do that, I would need to pick two equations to work with at a time until I have two equations with just the two letters x and y. So let's look, for example, at if I chose to look at equations 1 and 2. If I look at equations 1 and 2, in order to eliminate the z here, you would want to have a negative 3z and a positive 3z. So in order to change this negative 1 into a positive 3, I would need to multiply equation 1 by what number? That's right, negative 3. So if I do negative 3 times equation 1, this would become negative 3x, positive, because a negative times a negative is a positive, 6y, and then a negative 3 times a negative 1 is a positive 3z, and again a negative 3 times that negative 2 is a positive 6. Okay, so that's my new equation there. And similarly, if I just look at equation 2 and leave it the way it is, it should work just fine. So taking equation 2 just the way it is, I have negative x, I have positive 6y. Notice those do not cancel because they are not they are the same sign. They're not opposites. But the negative 3z and the positive 3z above will cancel. And I copy this 6 as well. Okay, so again, these will not cancel. So when I add those up, 6 and 6 is 12. So we're adding here. And then here we have 3z minus 3z, so those will cancel because they're opposites. So those are 0. But 6y plus 6y is 12y. And negative 3 and negative 1 is negative 4, so negative 4x plus 12y. Now you're welcome here to make your life a little easier. If you notice that all of these numbers are common multiples, right? You could divide by 4, for example, to have a nicer looking equation. So you don't have to, but if you notice it, it will make your life easier later. So if you divide by 4, you'd have negative 4 divided by 4 is negative 1x, 12 divided by 4 is positive 3y, and 12 divided by 4 is positive 3. Just makes your life a little bit easier. You don't have to do that, but eventually, I promise, life will be easier. Okay, so that says the same thing. So now we have an equation with just an x and a y from looking at 1 and 2 together. So I could now look at 1 and 3 together, or 2 and 3 together. How about we look at 1 and 3? Because that little negative z might be easy to work with. So if I look at equations 1 and 3, what would I need to do to those equations in order to make z go away? So with equation 1, what could I multiply it by so that when I add the z components, they cancel? It's already a negative 1 for its coefficient, and I have a positive 5 here. So I would like this to be a negative 5, meaning since it's already negative, I just need to multiply that equation by what number? Positive 5 is correct. So 5 times equation 1, but leave equation 3 the way it is, would give me 5x minus 10y, 5 times negative 2 is negative 10, minus 5z, because 5 times negative 1 is negative 5, and 5 times negative 2 gives me negative 10, right? Catch me if I make any mistakes, it happens. Equation 3, copy and paste carefully the right equation. We're looking at equation 3. Would be 2x minus 11y plus 5z equaling negative 11. Okay. So now we're going to do the same thing we did earlier. We're going to add these down and see that our z's should cancel because we built it that way. They are opposites. But negative 10, negative 11, that becomes negative 21. And 5 plus 2 is positive 7 here. So 7x. And again, negative 21y. So I'm getting 7x minus 21y equals negative 21. So this is another equation with just x and y. That's what we wanted to create. So now we have 2 of those. With those 2, we now have a new system that we can build. So our new system with just x and y would be negative x plus 3y equals 3. I'm going to put a little star so you can see where they came from. equals 3, and 7x minus 21y is equal to negative 21? Okay, so with that system, you can use substitution or elimination, whichever you prefer, to solve for x or y. All right. Now I'm going to use elimination. Again, substitution would be lovely, but I think elimination is quite nice in this case. If I wanted to eliminate, let's say, x, what would I need to multiply the first equation by in order for x to go away? That's right, 7. So if you multiply that equation by 7, you would get negative 7x, negative 21y, and 3 times 7 is 21. Okay, and below it here, I'm going to copy and paste just 7x minus 21y equals negative 21. Again, catch me if I make any errors. It happens. So at this point, I need to combine like terms by adding down. And notice this time the 7x and the negative 7x cancel, which was what I was hoping, so that's 0. But also the 21y's, are they going to cancel? Let's see. What happens here? I had positive, I think I copied a sign wrong, 7 times 3, if you didn't catch that. Watch me. That's 21. So those do cancel, all right? Those do cancel. So that's another 0. And the 21 minus 21, those cancel as well. Now, we did an earlier video, you might want to go back, where we had 0 equals a number which was false, meaning that the system was inconsistent. But when we get 0 equals 0 popping up in one of these steps, this is something which is always true, no matter what x is, no matter what y is, no matter what z is. And when you get something that's always true, you do have a solution, so it's still a consistent system, but that solution is going to depend on one variable, so it's going to be dependent. In other words, instead of a single point, you have a line where all 3 planes are coming together. So this is going to be a trickier situation where your solution set will still be an ordered triple, but it'll be all ordered triples of a certain type, where x and y are going to be solved in terms of another letter, z. So you could let z be your independent variable, if you will, and we're going to make x and y depend on that z. Okay? So you could have picked a different letter, like you could have made them depend on x or made them depend on y, but most students will choose to let them depend on z. So where do you go from here to get those expressions which depend on z? Good question. What you want to do is actually go back to one of these equations here, which is just in terms of the star equations, just in terms of 2 variables. And here, if you notice, we could have solved for x, for example. What would x have equaled? If we'd solved for x, it would be x equals 3y minus 3. What happens if we had solved for y, just for kicks and giggles? 3y would have equaled x plus 3, right? Notice that if I just move the x to the other side. So that would have meant solving for y, let's say, that would have meant dividing everything by 3, that y would equal, this is 1x, so 1 divided by 3, 1/3 x, and 3 divided by 3 is 1. Now, you might think that's not y in terms of z, that's y in terms of x, and you are correct, but hold on to that. If you go back now, after you solved one of these 2 equations for one variable, so we solved for y in terms of x, but you could have done x in terms of y, it doesn't matter to me. Then go back up to one of the equations above that had all 3 variables, pick the easiest one that you like, and we're going to replace every variable here, which is y, with what we have in our expression. So for example, if you go back to that first equation, equation 1 for example, we would have x minus 2 copies of y, and I'm going to say y equals my expression that I got right here. That expression was 1/3 x plus 1. And then the rest of the equation, equation 1, was minus z equals negative 2. Why am I doing this? I'm trying to find x in terms of z. Now notice I just have an equation with just x's and z's, so I can get all the x's on one side, all the z's on the other. So let's go ahead and do that. Distribute, and I have x minus 2/3 x. 2 times 1/3 is 2/3. Negative 2 times 1 is negative 2, minus z equals negative 2. Okay, we're trying to solve for x. So 1x minus 2/3 x. 1 minus 2/3 is 1/3. So I have 1/3 x. If I add negative 2 to the other side, it would be negative 2 plus 2, which is 0. So I have negative 1/3 x minus z equals 0. Or if you move z to the other side, you have 1/3 x equals positive z. So what does x equal then? Well, multiply both sides by 3, and you have that x equals 3z. Okay, so now we know what x equals. X in terms of z, x equals 3 times as much as z. What this means, if you're looking for ordered triples, whatever z is, x is 3 times as large. So if z is a 2, x is a 6. If z is a 4, x is a 12. It's 3 times as large as your z. Now we just need to find y, and this part should be pretty easy because we already have x, don't we? We already have x. So in order to find y, what is one thing that we could do? Well, we know that y equals 1/3 x plus 1. So let's come back up there and see what we get. Let me grab another color for you. How about red that works here? So once we already know what y is in terms of x, now we just need to replace our x in terms of z. So we have here y equals 1/3 whatever x is, add 1. But we know x in terms of z is 3 times as big as z. Okay, so now simply distribute there, or multiply I should say, and you get 1/3 times 3, which is 1. So y equals 1z, or just z, plus 1. So what does that mean? It means that if you know what z is, you're going to add 1 to it, and that will give you your y. So y is just 1 bigger than z. So let me clean that up a little bit here. So what we're saying is you have infinitely many points which are going to be solutions. Examples of these points could be, for example, let's say that x would be the point. Let me not use the braces because that's the whole system. So an example of one of these points would be an ordered triple, like if x was 2. Well then, sorry, if z was 2. So then x would be 3 times 2, which is 6, and y would be z plus 1. So 1 more than z, 2 plus 1 is 3. What's another ordered triple here that would be on the line of solutions? What if x was -1? Sorry, I keep saying x. What if z was -1? Well, then 3 times -1 would be -3. Z plus 1, so that would be -1 plus 1 would be 0. So that would be another point. So there would be infinitely many points like this as long as they obey this relationship, where your x component is 3 times as much as your z, and your y component is 1 larger than your z. So again, why did we have to go through that extra step of finding x and y in terms of z carefully? That was because we had a system where when we were trying to solve for just one variable at a time like normal, we ended up getting something which was always true, like 0 equals 0 or 2 equals 2. That's always going to be your telltale sign that you have a consistent but dependent situation. Okay? And in a matrix, which you'll see in future units, that will definitely mean you'll have a row where there's all zeros. 0 equals 0. Well, I hope this made a little bit of sense. It'll probably take some plays over and over again until it makes more sense for you. If you have any questions, please don't hesitate to reach out. Otherwise, happy practicing, because remember, math is not a spectator sport. I'll see you next time.